So now that we've walked through various operators in the mono class that we've been discussing, suppressing operators and transforming operators and scheduler operators and combining operators and so on, let's take a look at a case study, which is case study EX3, that will put it all together. And this particular case study is going to take a look at from callable, zip with, zip, flat map, do on success, subscribe on then, and parallel thread pool operators in order to demonstrate how those things can get used to do some pretty cool stuff. And as always, you can go and find the example here in my GitHub repository under the Reactive Mono EX3 folder. So we're now in my IntelliJ project for case study EX3. Let's go ahead first and take a look at the test driver program. As you can see, it's the main entry point is always into all the tests we're going to run to demonstrate these various features from the mono class. And there's going to register 3 methods: test fraction multiply async, test fraction combine 1, and test fraction combine 2. All of these are going to actually run asynchronously. So as always, we're going to start everything running by calling the async task barrier run task method, which sets the wheels in motion in ways we'll talk about later. And then the main thread of control is going to block until all the asynchronous computations are finished, in which case we'll print out how many things actually finished, which in this case should be all of them because there should be no exceptions. So let's go ahead and take a look at the actual implementation of this stuff. So here is mono EX. That's the implementation class. We have we have a field called sRandom that's just a random number generator that's used by a bunch of the different functions we're about to look at. So here's test fraction multiply async. As you can see, it creates a string buffer to store the results that we're going to print at the end. We use a string buffer because these things are taking place in the background, and string buffer is thread safe, unlike string builder, which is not thread safe. And then we're going to go ahead and make ourselves a big fraction asynchronously. So here's the factor method makes a big fraction asynchronously. You can see what it does is it uses the from callable factor method together with the make big fraction factor method. We've looked at this many times before. It makes a very large numerator, a much smaller denominator, and then it creates a big fraction by combining those two things together. And in this case, it will actually reduce the big fraction. And the reason for doing that is it's going to be running in a background thread, so it's okay to reduce it. It's going to take a while, but we're running in a background thread. How do we know we're running in a background thread, you asked? We're using subscribe on with the parallel scheduler. And so that means that this from callable method, remember how subscribe on works, it goes back to the beginning of the chain. The from callable method is a lazy method, so it'll run in the context of whatever subscribe on's thread pool will be, which is the parallel thread pool. So we're going to make this big fraction and reduce it in a background thread. And then when we're all done, we're going to use an action operator called do on success to append that big fraction to the end of the string buffer. So this thing can take however long it wants to run. It can take its sweet time, no big deal. Then what we're going to do, so keep in mind, this is going to return a mono to a big fraction right away. You'll get the mono back right away while the computation is running in the background. And then we say, hey, BFM1, which is this thing that's running in the background, whenever you happen to finish, please use flat map and go ahead and take the big fraction that was created asynchronously and then multiply it asynchronously. So let's go take a look at multiply async. And here's multiply async. Multiply async works very much like the creation factor method does. What it does is it takes 2 big fractions, and it's going to use from callable again to get it to run in the right context. It will then say big fraction 1 multiplied by big fraction 2, and run that in the parallel thread pool. So that will also run in the background. And that will return a mono to a big fraction, and we'll see what we're going to do with that big fraction in a second after it completes. So we get back BFM2, which is the big fraction it's the mono to the big fraction that's being multiplied in the background. Note that if we used map instead of flat map, then we would have had a mono to a big fraction, which would have worked, but it would have been very much ugly and convoluted, so we didn't do it that way. What we do then is we say, when big fraction 2 completes, then on its success, go ahead and display the mixed big fraction. We pass in the big fraction and the string buffer rather. And you can see what it does is it appends the big fractions results as a mixed string to the string buffer, and then it displays the string buffer as a string. So just a helper method to do that. And the final thing we do here is we return an empty mono saying, we're done, async task barrier framework, you can consider us complete. And so if we're the last thing that was running asynchronously, then the whole thing is complete. Obviously, if there's other things running asynchronously, we have to wait for them to be done. So now let's go take a look at a much more interesting example. This is called test fraction combine 1. Once again, uses a string buffer because we're running in the background and doing some operations to this in the background. We want it to be thread safe. We're going to use our big fraction async factory method twice now. So we get back 2 big fractions that are being created in the background, 2 monos to big fractions, M1 and M2. And then what we're going to do a whole bunch of wacky stuff here. We're going to take M1, and when M1 completes, then we're going to multiply the results of M1 by some big reduced fraction. And that's going to take place in the background. So we're going to kick that off. And then we're going to use zip with such that when the multiplication of M1 completes and the original creation of M2 completes, which might occur a little faster, but whatever. When both the results of multiplying the result of M1 asynchronously completes and the creation of M2 completes. So now we have 2 results, one that was multiplied and one that was just created. We're then going to go ahead and multiply the second big fraction asynchronously. So when that completes too, so all this stuff is running, and when everything completes, then we're going to add all the results together. And the last thing we're going to do is we're going to display this as a mixed big fraction when everything succeeds, and we'll return the mono to void, indicating to the async task barrier framework that we're done with the asynchronous computation, so it can shut itself down if it's appropriate. So the key point to remember here is there's a lot of asynchrony going on here. We're waiting for M1 and M2 to finish. When M1 finishes, we multiply it by a big fraction. When M2 finishes, we multiply it asynchronously by a big fraction. And when all that stuff is done, we add the results together. All right, so that's using zip with. Remember, zip with wants 2 monos, one that's the mono that the zip with method is called on, and the second is the mono that's the first parameter. Both of those have to finish before we can continue. The problem is if you've got a bunch of big monos, you can get some really ugly nested calls. This is deeply nested enough, to be honest with you. We'd like to not have such deep nesting. So to demonstrate how to avoid deep nesting, we're going to apply yet another example. This is called test fraction combine 2. It's just the second combine example. It uses a string buffer as always. But in this case, we're going to make 3 big fractions that are being created asynchronously. And I could have done more than 3. I just figured that 3 was more than 2, which is what we've done before. Once you get past 2, you'll see why we're going to do what we're doing, because we have to generalize, because we can't just pass like one parameter and then have the object that's the caller for zip with. So we get M1, M2, M3. I think you know by now they're all just going to be big fractions that will be ready when they're all finished being created. And then we're going to create something called a combinator. And we'll look at this in more detail in a second. I don't want to talk about this yet until I show you how this all gets used. And this is completely insanely cool. So check this out. We're now going to come down here. This is so much fun. And we're going to make ourselves an array of monos to big fractions. And inside that array of monos to big fractions, we're going to say when M1, M2, and M3 complete, take their results by using flat map and multiply them asynchronously by this big reduced fraction constant. So we're making an array of monos to big fractions, which will have the results when those other things complete. So you kind of have like nested monos going on here, right? And then what we're going to do, so keep in mind, the whole point of this was to avoid that weird nesting that we ended up with here in the control flow that we used with zip with, where you have to keep kind of chaining these things together. It kind of runs off the page eventually to the right as you go deeper and deeper into the nesting. So now we're going to create an array of monos to big fractions, all of which are running asynchronously. And we're going to take that array of big fractions, all those asynchronous multiplications that are all taking place now in the background, and we're going to pass it to the zip method. So we're going to say zip, here's an array of big fraction or monos to big fractions that are running asynchronously. And I want you to wait for all those things to be done. And of course, we could have more than 3. I just chose 3 to keep it simple. And after all those computations are done running, apply the combinator to the results. And then give me back a single mono that when it completes, in this case, we're going to go ahead and display the resulting mixed big fraction. So let's go take a look at the combinator. Now that we've kind of seen how it gets used, we can take a look at what it does. It's completely and totally insane. So the combinator is a function that takes an array of objects, and in this case, a big fraction. It'll return the big fraction. Now, just for kicks, we could have done this with using Project Reactor methods, but I thought it was actually cleaner and easier to use just a Java stream. So what we do here is we say, take this big fraction array. So this is an array of objects. So we say BF array, which is this array of objects, untyped, the root of all classes in Java. We say, create that array or convert that array into a stream. So now I have a stream of objects. And then what I'm going to do is I'm going to take each of those objects, and because I know the type that I want to deal with here, I'm going to convert them into a stream of big fractions. So I'm going to take each of those objects, cast it to a big fraction, and then turn it into a big fraction. This is just syntactic. I don't quite know why they had to do this. It probably has something to do with the use of generics and generic arrays in Java, which are somewhat typeless and so on. So you couldn't have what you want to be able to do here, what you'd like to be able to say is big fraction. You'd like this to be able to take a big fraction array, but that won't work. And if we try to do that, things will blow up. So we're going to have to go back to an object array. And then what we're going to do is we're going to say, take that stream of big fractions that we got out of the array and reduce it. This is using the Java streams reduce, which says add all the elements together. So take each of the elements that's in that array and add them up, and then return that as a big fraction. That's what this parameter is here. So that's what's coming back as the result of all this stuff. Again, there's other ways to do it. I just thought this was a nice use of streams. Very simple, very concise. So basically what it's saying is after all the asynchronous operations have completed, zip will call the combinator, and the combinator will take this array of objects that correspond to the results, and we know what their real types are, and it'll go ahead then and will allow us to do something to each of those elements, which in this case is to add them together. So I think you'll agree with me that, number one, this is like really, really powerful, insanely powerful, very consistent. You don't have all this weird nesting that's trickling off the right-hand side of the page. And it can generalize to whatever you want. And we're basically making an array of asynchronous operations that are going to run in the background. The question is, why do we have this unchecked? And it just has to do with the insane type system of Java, where things that are arrays of non-objects are somewhat less well treated as first-class citizens in the type system. And there's the reason, honestly, is there's no other way to make it work. If we take this thing out, then we're going to end up with a warning here. It'll yell at us and tell us it wants us to do all kinds of crazy things to this stuff. And none of those things work. So we know that this is actually type safe, but the compiler doesn't think it's type safe. So we have to tell it. We have to tell the IDE, we know what we're doing. Trust me. It's kind of like putting a cast in where you're like, yeah, I know. These are two different types, but I know what I'm doing, so just believe me, please. Yeah, the observation is a book by a guy named Josh Block called Effective Java, and he talks about some of the tricks you have to work with and the techniques and idioms you have to know in order to kind of work around the weird type system. Bottom line is Java's generics are not as powerful and well thought out as C++'s template. And there's a bunch of weirdnesses with generics, and it has to do with something called type erasure. And it's very weird, and it basically came down to them wanting to be able to support generics in Java without having to change Java bytecodes and the Java virtual machine, which in hindsight made sense from a portability point of view, but they could have made life better if they'd actually thought it through a bit more. And I think other languages that have come later, like Kotlin, probably do a better job of dealing with that. But we're stuck with Java for its quirks. And it does work pretty well. It's just kind of quirky. Okay, so I think those are the methods that we're talking about in this particular context for this example. Pretty cool example, non-trivial example, very, very powerful. And you're learning things here that are almost impossible to find on the web. I had to do a lot of experimentation to get all these things to work. And reading the documentation provided very little insight, and the little examples you'll find on Stack Overflow give you a little bit of help, but this is really a nice way to see how all the pieces fit together.